Hello and welcome to the sleepy universe. Asterisk, as the day gently fades, and the world outside begins to quiet its busy hum, you find yourself drifting into a space of stillness. The sounds of the day recede, becoming soft echoes in the distance. Breath deepens, a soft, slow rhythm, like the quiet lapping of waves on a distant shore, or the gentle sigh of the wind through ancient trees. Feel the peaceful weight of your body sinking deeper into comfort, deeper into rest. This moment, this quiet space, is yours tonight. We embark on a journey not through distant lands or across vast oceans, but into the very heart of the cosmos, to its most profound and enigmatic mystery. We will turn our gaze towards a phenomenon so extreme, so powerful, that it challenges our very understanding of space, time, and reality itself. We are going to explore black holes, those silent, cosmic abysses that beckon with an irresistible pull, hinting at secrets beyond our wildest dreams. Imagine, if you will, a place in the universe where gravity reigns supreme, where its invisible hand is so incredibly strong that nothing, not even light, can escape its grasp. It's not a hole in space, as the name might suggest, but rather an incredibly dense concentration of matter squeezed into an impossibly small volume. Think of taking something as massive as our sun and compressing it down to the size of a small city. The result would be a black hole, a region of space-time so warped and curved that it becomes a one-way street as you lie here. Comfortable and still, allow your mind to gently open to this extraordinary idea. It is not about magic, not about science fiction, but about the deepest, most fundamental rules of our universe, pushed to their absolute limits. These cosmic giants, though they appear dark and empty, are in fact among the most powerful and active objects in the cosmos, constantly shaping the galaxies around them. Consider a familiar image, a whirlpool in a river. As water spirals inward, it moves faster and faster, until at its very center, nothing can resist its pull. A black hole is like a cosmic whirlpool, but instead of water, it's space-time itself that is swirling inward, faster and faster, drawing everything towards its unseen center. Anything that crosses a certain boundary, anything that gets too close, is destined to fall in, never to return. That irresistible pull is not something you can see directly, for black holes are, by definition, dark. They emit no light, reflect no light, and shine no light. They are truly invisible, detected only by their profound influence on the matter and light around them. We see their presence by the way stars orbit them, by the way gas heats up and glows brightly as it spirals inward, or by the way they stretch and distort the very fabric of space and time around them as you continue to breathe, deeply and evenly. Imagine the sheer scale of this gravitational power. It's a force so immense that it can tear apart stars, accelerate gas to incredible speeds, and even warp the paths of light rays, causing distant galaxies to appear distorted, like looking through a funhouse mirror. This is gravity in its most extreme form, a cosmic sculptor, shaping the universe with an invisible, powerful hand. These black holes are born from the spectacular deaths of the largest stars. When a massive star, many times larger than our sun, runs out of fuel, it can no longer support itself against its own immense gravity. It collapses inward, crushing its core down to an incredibly dense point. This catastrophic collapse is one of the most violent events in the universe, a magnificent fiery end that gives birth to a silent, dark enigma. Let this thought settle gently in your mind, like a soft blanket settling over you. The universe is a place of incredible extremes, of immense beauty and profound power. And black holes are perhaps the ultimate expression of this power, a testament to the fundamental forces that govern all of existence. They are not just objects in space. They are regions where space and time become so profoundly warped that they take on properties unlike anything we experience in our daily lives. The idea of a black hole might seem frightening, a place of no return. But in our journey tonight, we will approach them with gentle curiosity, understanding that even in their extreme nature, they hold clues to the universe's deepest secrets. They are like cosmic laboratories, where the laws of physics are pushed to their breaking point, offering scientists a unique opportunity to test our understanding of gravity, space-time, and the very nature of reality as you drift. Imagine the quiet presence of these cosmic abysses scattered throughout the universe. Some are relatively small, born from individual stars. Others are supermassive, millions or even billions of times the mass of our Sun, residing at the very centers of galaxies, including our own Milky Way. They are the silent anchors of cosmic structures, holding billions of stars in their gravitational embrace. This irresistible pull, this profound warping of space-time, is what makes black holes so fascinating. It's what allows them to bend light, to stretch objects, and most astonishingly, to affect time itself. The closer you get to a black hole, the more profoundly time behaves in ways that defy our intuition. It slows down, stretches out, a relative lullaby sung by warped Spaghettification. Feel the quiet hum of the night and the gentle rhythm of your own breath. Just as the universe holds these immense, mysterious objects, so too does it hold countless wonders waiting to be discovered. Black holes, in their silent power, are a reminder that reality is far more complex and awe-inspiring than we often perceive. They are a testament to the universe's capacity for elegance, even in its most extreme forms. Rest now in the knowledge of this profound mystery. The universe is a place of endless wonder, and even its darkest corners hold secrets that illuminate the very nature of existence. Let the quiet understanding of this cosmic abyss guide you deeper into peaceful slumber. For as we approach these dark giants, we will encounter a boundary, an invisible line, beyond which there is no return, a point where light itself can no longer escape. This is the event horizon, and it is here that the universe's rules truly transformed as you continue to drift, softly, deeply. Allow your mind to journey closer to the heart of a black hole's mystery. We have imagined its immense gravitational pull, its silent beckoning from the cosmic abyss. Now we approach a specific, invisible boundary, a shimmering veil that marks the point of no return. This is the event horizon, a concept as profound as the black hole itself. Imagine yourself floating gently in space, far from any star or planet, in the quiet darkness between galaxies. Ahead, you sense the presence of a black hole, not by sight, but by the subtle bending of starlight around it, like a faint lens distorting the distant cosmos. As you drift closer, the pull of its gravity becomes more noticeable, a gentle tug drawing you inward. The event horizon is not a physical surface, like the surface of a star or a planet. You wouldn't feel a bump or a wall if you crossed it. Instead, it is a boundary in space-time, an invisible line of no return. Think of it like the edge of a waterfall. As water flows towards the edge, it moves faster and faster. Once it crosses that edge, it is irrevocably committed to falling down, no matter how hard it tries to swim back upstream. The event horizon is precisely this kind of edge, but for everything, including light. This is the place where light itself can no longer escape. Imagine a beam of light shining outward from just inside the event horizon. The space-time fabric is so incredibly warped and curved inward that even if the light beam points directly away from the black hole, it is still swept inward, pulled back by the overwhelming gravity. It's like trying to run upstream on a river that is flowing faster than you can run. No matter how fast you sprint, the current carries you backward. So, if you were to cross the event horizon, you wouldn't see a giant exit sign disappear behind you. Instead, the light from outside the black hole would still reach your eyes. But any light you emitted, any signal you sent, would be trapped. From the perspective of someone far away, observing you, you would appear to slow down, to freeze it. The edge, your light dimming and reddening until you seemed to vanish, forever trapped in a moment of time. This shimmering veil of no return is a one-way membrane. Everything can fall in, but nothing can come out. It is the ultimate cosmic trap, a boundary where the universe's rules transform, forever changed. Inside the event horizon, the very concepts of in and out become warped. What we perceive as forward in time outside becomes inward in space inside. The path towards the singularity, the black hole's center, is no longer just a direction in space. It becomes an inevitable future. As you breathe, softly and deeply, let this profound idea settle. The event horizon is not a barrier of matter, but a boundary of space-time. Its size depends on the mass of the black hole. A black hole with the mass of our sun would have an event horizon only about 6 kilometers, 4 miles across. A supermassive black hole, billions of times the sun's mass, could have an event horizon larger than our entire solar system. Consider a swimmer caught in a powerful current. As they approach a drain, the water moves faster and faster. There's a point where, no matter how strongly they swim against the current, they will inevitably be pulled down the drain. That point is the event horizon. Once crossed, the path inward is no longer a choice. It is the only possible direction, the unavoidable future. This transformation of rules beyond this edge is what makes black holes such extraordinary laboratories for physics. Inside the event horizon, our familiar notions of space and time become profoundly intertwined and distorted. The dimension of time, which we usually experience as a forward progression, points inward towards the singularity, and the spatial dimensions, which we usually can move freely within, become fixed, pointing only towards the center. This means that once you cross the event horizon, you cannot turn back, not because there's a physical barrier, but because the very fabric of space-time is pulling you inward faster than you can move in any other direction, faster than light itself can travel outward. It's as if the entire universe inside that boundary is tilting, sending everything inevitably towards the center. Feel the quiet, inexorable pull of this concept. The event horizon is a boundary of ultimate commitment. Everything that crosses it is destined for the singularity, the incredibly dense point at the black hole's heart. There is no escape, no turning back, no communication with the outside world once that shimmering veil has been breached. It is the universe's ultimate point of no return. Scientists study the event horizon not by going there, but by observing its effects from afar. They look at the behavior of matter spiraling into black holes, the intense X-rays and gamma rays emitted as gas heats up to billions of degrees just before crossing the boundary. They use powerful telescopes to image the shadow cast by the event horizon against the glowing matter around it. providing direct visual evidence of this profound boundary. As you drift deeper into slumber, allow your mind to contemplate this invisible edge. It is a place of profound transformation, where the very rules of the universe shift. It is the gateway to a realm where our familiar understanding of reality is turned inside out. The event horizon is a silent, cosmic threshold, a testament to gravity's ultimate power. This profound edge, this shimmering veil, is where the gentle pull of gravity becomes an irresistible force, drawing everything inward. And as we continue our journey, we will explore the terrifying, yet fascinating, consequences of this immense gravitational embrace, as objects are stretched and pulled in a cosmic dance of spaghettification. Asterisk, as you continue to drift, softly, peacefully, let your mind now venture beyond the event horizon, into the realm where gravity's power becomes truly unimaginable. We have approached the point of no return, that invisible boundary where light itself is trapped. Now, we explore the terrifying, yet fascinating, consequence of falling deeper into a black hole's gravitational embrace, a phenomenon known as spaghettification. Imagine, for a moment, a long, thin strand of something familiar, like a piece of spaghetti. Now, picture that piece of spaghetti being stretched longer and thinner, pulled from both ends with incredible force. This is the essence of spaghettification, a term scientists use to describe what happens to any object, whether it's a star, a planet, or even a hypothetical astronaut, as it falls into a black hole. The immense, stretching force comes from the extreme difference in gravity across an object near a black hole. Gravity is not uniform. It pulls much, much stronger on the parts of an object that are closer to the black hole's center than on the parts that are farther away. Think of it like a giant rubber band, pulling harder on your feet than on your head if you were falling, feet first, into a black hole. As you draw near, this differential gravity, also known as tidal forces, pulls with unimaginable power, elongating all that enters. If you were falling feet first, your feet would feel a much stronger gravitational pull than your head. This difference in force would stretch your body lengthwise, making you longer and thinner, like that piece of spaghetti. At the same time, the gravity pulling on your left side would be slightly different from the gravity pulling on your right side, causing you to be squeezed inward, becoming narrower. This is a dance of cosmic proportions, a final, irreversible stretch. A star approaching a black hole would not simply be swallowed whole. Instead, as it gets too close, the side of the star facing the black hole would feel a much stronger pull than the side facing away. This immense tidal force would literally tear the star apart, ripping it into long, luminous streams of gas that spiral inward, creating a spectacular cosmic light show visible across galaxies. Feel the quiet intensity of this gravitational embrace. For smaller black holes, like those formed from the collapse of a single star, the spaghettification forces would be incredibly strong even before you cross the event horizon. You would be stretched and torn apart long before you reach the point of no return. This is why falling into a stellar-massed black hole would be an incredibly violent and swift end. However, for supermassive black holes, those giants at the centers of galaxies, the situation is subtly different. Because their event horizons are so much larger, the change in gravity across your body at the event horizon would be much more gradual. For a supermassive black hole, you could theoretically cross the event horizon without feeling the immediate effects of the stretching would become significant only as you got much, much closer to the singularity at the very center. This means that while spaghettification is an inevitable fate for anything falling into a black hole, when it happens relative to the event horizon depends on the black hole's size. For smaller ones, it's a violent tearing before entry. For supermassive ones, it's a slow, agonizing stretch after entry, as you inevitably plummet towards the singularity. As you breathe, softly and deeply, let this profound image settle. It's a reminder of the extreme conditions that exist in the universe, conditions that push the laws of physics to their absolute limits. The dance of spaghettification is a testament to gravity's ultimate power, its ability to reshape matter in ways that are both terrifying and scientifically fascinating. Consider a piece of taffy being pulled apart. As it stretches, it becomes thinner and longer. The forces are concentrated, drawing the material out. Spaghettification is this process on a cosmic scale, powered by the most extreme gravitational gradients in the universe. It's a final, irreversible stretch, a transformation into an elongated stream of fundamental particles. Scientists don't observe spaghettification directly, but they see its telltale signs. When a star gets too close to a supermassive black hole, they observe tidal disruption events where the star is ripped apart and its gas spirals inward, creating flares of light that can last for months or even years. These observations are powerful evidence of gravity's immense stretching power. Near black holes, as you drift deeper into slumber, allow your mind to contemplate this cosmic embrace. It is a place where the familiar solidity of objects gives way to an extreme elongation, where matter is reshaped by the unseen hand of gravity. It is a profound and humbling reminder of the universe's capacity for both immense beauty and overwhelming force. This dance of cosmic proportions, this final, irreversible stretch, is one of the most dramatic consequences of a black hole's gravity. But even more mind-bending than the stretching of matter is the stretching of something far more fundamental: time itself. For as we continue our journey, we will explore how time's whisper slows. Near the black hole's edge, a relativistic lullaby, sung by warped space-time. As you continue to drift, softly, peacefully, let your mind now turn to the most astonishing effect of a black hole's immense gravity, its profound influence on time itself. We have explored the irresistible pull, the point of no return, and the stretching embrace of spaghettification. Now, prepare to listen closely, for time itself begins to slow, a gentle, relativistic whisper near the black hole's edge. Imagine a clock ticking steadily. In our everyday world, time flows uniformly for everyone. A second is a second, a minute is a minute, no matter where you are or how fast you're moving. But this is not true near a black hole. According to Albert Einstein's theory of general relativity, immense gravity warps not only space but also time. The stronger the gravity, the slower time flows. So if you were to approach a black hole carrying a clock, an observer far away would see your clock ticking slower and slower as you got closer to the event horizon. Your movements would appear to slow down, your voice would deepen, as if caught in slow motion. From their perspective, your moments would stretch into eternities. It's a profound and almost poetic effect, a relativistic lullaby sung by warped space-time. Think of it like walking through thick honey. Every step you take, every movement you make, would be slowed down. The honey is like the intense gravity of the black hole, making it harder for time to flow at its usual pace. The closer you get to the black hole, the thicker the honey becomes, and the more dramatically time slows down for you. Relative to someone in a weaker gravitational field, this means that if you were to send a signal, say a flash of light, every second from your position near the black hole, An observer far away would receive those flashes at increasingly longer intervals. What feels like 1 second to you might be 2 seconds, then 10 seconds, then a minute, then an hour, then a day, then a year for the distant observer. From their perspective, you would appear to slow down, to freeze at the event horizon, your light dimming and reddening until you seemed to vanish entirely, forever trapped in a single, stretched moment. This bending of the very fabric of existence, this warping of space-time, is one of the most mind-bending predictions of general relativity, and it has been confirmed by numerous observations. For instance, the atomic clocks on GPS satellites, which orbit Earth in a weaker gravitational field, tick slightly faster than clocks on the ground. To ensure GPS accuracy, these tiny differences in time flow must be accounted for. Near a black hole, this effect is amplified to an extreme degree. As you breathe softly and deeply, let this profound idea settle. Time is not an absolute, unchangeable river flowing uniformly for everyone. It is a dimension, like space, that can be stretched and compressed by gravity. Near a black hole, the gravitational pull is so extreme that it creates a kind of time well, where time literally runs slower. Consider a film reel. If you play it at normal speed, time flows as we know it. But if you slow the reel down, the events on screen stretch out, taking longer to unfold. For someone far away from a black hole, observing you approach it, it would be like watching your life unfold on a film reel that is constantly being slowed down, until eventually it appears to stop entirely at the event horizon. This phenomenon is why, theoretically, an astronaut falling into a black hole would never actually be seen to cross the event horizon by an outside observer. They would simply appear to freeze and fade away at the edge, their light taking an infinite amount of time to reach the distant observer. For the astronaut themselves, however, time would continue to flow normally, and they would cross the event, the horizon, without noticing anything particularly special about that moment, only to face the inevitable spaghettification inside. As you drift deeper into slumber, allow your mind to contemplate this relativistic lullaby. It is a place where moments stretch into eternities, where the very rhythm of existence can be profoundly altered by gravity. It is a testament to the universe's capacity for surprising and counterintuitive phenomena. This bending of the very fabric of existence, this profound influence on time, is what makes black holes so unique. It's a reminder that our perception of time is deeply linked to our position in the universe and the gravitational forces acting upon us. The next time we meet in this quiet space, we will explore what such extreme time warping might mean for what you would actually see if you were at the edge of a black hole. As we delve into the distorted reality of the view from the edge, as you continue to drift, softly, peacefully, let your mind now imagine the most extraordinary sight in the universe, the view from the very edge of a black hole. We have explored how gravity slows time and how objects are stretched. Now, we consider how light itself is profoundly bent, creating a reality that is twisted, compressed, and utterly unlike anything you have ever seen. Imagine yourself floating just outside the event horizon, the invisible boundary of no return. You are not yet pulled in, but the black hole's immense gravity is already profoundly warping the space-time around you. In our everyday world, light travels in straight lines, but near a black hole, space-time is so curved that light rays are bent, twisted, and even looped back on themselves. So, the view from the event horizon's brink would be a distorted reality. The stars behind the black hole, which should be hidden from view, would appear above and around it, their light having been bent around the black hole's immense mass. You might see multiple images of the same distant galaxy, its light having taken different paths around the warped space-time, creating a cosmic mirage. Think of looking through a glass sphere or a funhouse mirror. The images you see are stretched, squeezed, and inverted. The black hole acts like a giant, cosmic lens, but one that is so powerful it distorts the entire universe around it. The light that reaches your eyes would have traveled along incredibly curved paths, giving you a panorama that is both breathtaking and deeply unsettling. As you draw closer, the sky would begin to change dramatically. The light from the entire universe, from all the stars and galaxies behind you, would be squeezed into a progressively smaller and smaller circle directly above you. It would be like looking through a tiny peephole and seeing the entire cosmos compressed into that small window. The rest of the sky would be utterly black, dominated by the black hole's shadow. This means the universe appears twisted, compressed, a final, strange panorama. The stars and galaxies that once filled the entire sky would be crammed into a tiny, intensely bright ring of light encircling the black hole's dark silhouette. This is the photon sphere, a region where light can orbit the black hole in unstable circles. If you were exactly at the photon sphere, light from behind your head could orbit the black hole and come back to your eyes, allowing you to see the back of your own head. As you breathe softly and deeply, let this profound image settle. The view from the edge is a testament to gravity's artistic hand, its ability to sculpt and reshape the very fabric of light and space. It's a sight that challenges perception, forcing us to abandon our intuitive understanding of how light travels and how space is structured. Consider a fish in a fish bowl. From the fish's perspective, the world outside the bowl is distorted, curved, and magnified by the glass and water. The black hole's gravity creates a similar kind of distortion, but on a cosmic scale, bending the very glass of space-time. For an observer falling into the black hole, the view would be even stranger. As you crossed the event horizon, you wouldn't see the universe suddenly disappear. Instead, because light from outside can still fall in, you would continue to see the light from the universe, but it would be increasingly redshifted and blue, stretched and compressed, until it became an unrecognizable blur. The light from behind you would be pulled forward, allowing you to see the entire history of the universe unfolding in front of your eyes, compressed into the final moments before you hit the singularity. This is a view that challenges perception, revealing gravity's artistic hand in its most extreme form. It's a reminder that reality is not fixed, but is relative to your position and the gravitational forces acting upon you. The light, the stars, the galaxies, all become part of a grand cosmic illusion, painted by the immense curvature of spaced ineth. As you drift deeper into slumber, allow your mind to contemplate this distorted reality. It is a place where the familiar rules of optics and perspective are utterly transformed, where the universe reveals its most surreal and breathtaking visual effects. It is a profound and humbling reminder of the universe's capacity for both immense beauty and overwhelming force. This final, strange panorama is a testament to the fact that black holes are not just empty voids, but active regions of space-time, where the laws of physics are pushed to their breaking point. But what lies beyond this distorted view, beyond the event horizon, at the very heart of the black hole? As we continue our journey, we will delve into the ultimate compression, the heart of nothingness inside the singularity. As you continue to drift, softly, peacefully, let your mind now venture into the deepest, most mysterious core of a black hole. We have explored the event horizon, the point of no return, and the terrifying stretching of spaghettification and the distorted view from the edge. Now, we journey beyond all of that to the very center, to a place where our understanding of physics breaks down, the singularity. Imagine taking all the matter that formed a massive star, or even billions of stars, and compressing it down to an infinitesimally small point, a point with no volume, yet containing all the mass. This is the singularity, the heart of nothingness, a place where density becomes infinite, and the curvature of space-time becomes boundless. Beyond the horizon, all paths lead inward, inevitably, to this single point. Once you cross the event horizon, the singularity is no longer just a location in space. It becomes your unavoidable future. Just as you are always moving forward in time, inside a black hole, you are always moving towards the singularity, no matter what direction you try to go in space. It is the universe's ultimate compression, a point where everything that falls in is crushed out of existence as we know it. Think of a funnel, narrowing endlessly to an infinitely small point. Everything poured into the funnel is drawn inexorably towards that point. The singularity is like this, but for the very fabric of space-time. It is a point where the laws of physics, as we currently understand them, simply cease to apply. Our equations break down, giving us infinite values, signaling that we have reached the limits of our current knowledge. This is the heart of nothingness, not because it's empty, but because all the matter that formed the black hole and all the matter that has ever fallen into it is concentrated there. It's a point of infinite density, where the very fabric of space and time are so profoundly warped that they cease to have meaning. The concepts of up and down, left and right, before and after lose their relevance. As you breathe softly and deeply, let this profound mystery settle. The singularity is not a place you can visit and return from. It is the ultimate destination for anything that crosses the event horizon, a point of no escape, no information, and no discernible structure. It represents the limit of our current physical theories, a frontier where new physics is needed to truly understand what happens. Consider a map. If you follow a path on a map, you can always find your way. But imagine a map where, at a certain point, all the lines converge into a single, infinitely dense dot, and beyond that dot, the map simply ends. The singularity is like that dot, a point beyond which our current map of physics cannot guide us. For decades, scientists have grappled with the implications of the singularity. Does it truly mean infinite density? Or does it mean that at such extreme conditions, new, unknown laws of physics emerge, preventing true infinities? Some theories, like quantum gravity, attempt to resolve this, suggesting that perhaps at the Planck scale, an unimaginably tiny distance, space-time itself becomes quantized, preventing a true point-like singularity. But for now, the singularity remains a profound mystery at its core. It is the ultimate endpoint of gravitational collapse, a place where matter is compressed beyond all recognition, and where the very fabric of space-time is torn. It is a reminder of the universe's capacity for extremes, for pushing the boundaries of what we can imagine. As you drift deeper into slumber, allow your mind to contemplate this heart of nothingness. It is a place of ultimate compression, where all distinctions vanish, and all matter becomes one with the warped fabric of space-time. It is a humbling reminder of the vastness of the unknown that still exists within the cosmos. This profound mystery At its core is what makes black holes so endlessly fascinating to scientists. They are not just cosmic vacuum cleaners. They are cosmic laboratories, where the laws of physics are pushed to their breaking point, offering tantalizing clues about the fundamental nature of gravity and the universe itself. But even these ultimate destroyers have a hidden role, for beyond their power to compress and consume, black holes are also silent architects, shaping galaxies and influencing starbirth. As we continue our journey, we will explore this surprising role, discovering how these dark giants contribute to the grand design of the cosmos. Asterisk, as you continue to drift. Softly, peacefully, let your mind now consider a surprising truth about black holes. We have explored their immense gravitational pull, their event horizons, and the terrifying singularity at their core. They seem to be ultimate destroyers, cosmic traps from which nothing escapes. Yet, these dark giants are not just destroyers, but also silent architects, shaping the universe in profound and unexpected ways. Imagine a colossal, unseen hand, gently guiding the swirling dance of billions of stars, influencing the birth of new suns and nurturing the growth of entire galaxies. This is the hidden, powerful hand of supermassive black holes. At the heart of nearly every large galaxy, including our own Milky Way, lies one of these colossal giants, millions or even billions of times the mass of our Sun. These supermassive black holes are the gravitational anchors of their galaxies. Their immense gravity sculpts the universe, holding billions of stars in their embrace, preventing them from flying off into the vast emptiness of intergalactic space. Without these central behemoths, galaxies might not have formed, or would have dispersed long ago. They are the quiet, powerful centers around which entire cosmic cities revolve. Think of the central pillar of a grand carousel. The pillar itself doesn't move, but its presence dictates the graceful, swirling motion of all the horses and carriages around it. The supermassive black hole is like this central pillar, its immense, unmoving gravity orchestrating the complex dance of stars, gas, and dust within its galaxy. But their influence extends beyond simply holding galaxies together. Black holes also influence starbirth. As gas and dust spiral inward towards a supermassive black hole, they get incredibly hot and emit powerful jets of energy and radiation. These jets, though destructive in their immediate vicinity, can also push gas and dust outwards, compressing it in other regions of the galaxy. This compression can trigger new waves of star formation, creating nurseries for future suns. So, while they consume matter, they also play a role in the creation of new stars, nurturing cosmic growth in distant regions. It's a paradox. Destruction leading to creation, a balance of forces that shapes the evolution of galaxies over billions of years. They are like cosmic gardeners, pruning and shaping the galactic landscape, sometimes violently, sometimes subtly. As you breathe softly and deeply, let this profound idea settle. Black holes are not just passive gravitational wells. They are active participants in the grand cosmic narrative. Their outflows of energy can regulate how quickly stars form in a galaxy, preventing too many stars from forming too quickly and consuming all the available gas. This feedback mechanism ensures a more balanced and sustained period of star formation, allowing galaxies to evolve over vast stretches of time. Consider a giant cosmic engine. The black hole is not just a drain. It's a powerful exhaust system, expelling energy that influences the surrounding galactic environment. This energy can heat up gas, preventing it from cooling and collapsing to form new stars, thus regulating the galaxy's growth. Or, as mentioned, it can compress gas, sparking new star formation. It's a delicate and complex interplay. Scientists study these cosmic architects by observing the powerful jets of energy they emit, the glowing disks of gas spiraling into them, and the precise orbits of stars around galactic centers. These observations provide compelling evidence for their profound influence on galactic evolution, revealing a hidden, powerful hand in creation that was once unimaginable. As you drift deeper into slumber, allow your mind to contemplate this surprising role. Black holes, in their silent power, are not just endpoints of collapse, but vital components in the universe's ongoing story of creation and evolution. They are a testament to the intricate balance of forces that governs the cosmos, where even the most destructive phenomena play a role in building something new. This hidden, powerful hand in creation is a reminder that the universe is full of unexpected connections and paradoxical roles. The very objects that seem to consume everything also contribute to the grand design, shaping the cosmic landscape in profound ways. But even from these dark giants, there are whispers of escape, a faint glow that hints at a subtle exchange with the universe. As we continue our journey, we will explore this astonishing idea, delving into the concept of Hawking radiation, a tiny glimmer of warmth from the cold abyss. As you continue to drift, softly, peacefully, let your mind now turn to one of the most astonishing ideas ever conceived about black holes. We have explored their immense gravity, their inescapable event horizons, and their role as cosmic architects. Now, we consider a concept that seems utterly paradoxical: the idea that black holes, despite their reputation as ultimate traps, might actually evaporate over incredibly long periods, emitting a faint glow. Imagine a perfectly dark room, seemingly devoid of any light. Now, listen very closely. Can you hear a faint whisper, a tiny glimmer of escape from the dark? This whisper is the theoretical phenomenon known as Hawking radiation, named after the brilliant physicist Stephen Hawking, who first proposed its existence. Hawking's groundbreaking work suggested that black holes are not perfectly black. Instead, they slowly leak energy, emitting a subtle glow of particles. This is a paradox of warmth from cold, a truly counterintuitive idea. If nothing can escape a black hole, how can it emit anything? The explanation is rooted in the strange world of quantum mechanics, particularly the concept of the quantum vacuum we explored earlier. Remember, the vacuum of space is not truly empty. It is a bustling sea of virtual particles constantly popping into existence and annihilating each other in pairs. A particle and its antiparticle. These pairs exist for an infinitesimally brief moment, before vanishing back into the vacuum. Near the event horizon of a black hole, something extraordinary can happen to these virtual pairs. Sometimes, one particle of a pair falls into the black hole, while its partner escapes. When this happens, the escaping particle carries away a tiny amount of energy from the black hole itself. It's as if the black hole is slowly losing mass, bit by bit, through this subtle emission. Think of it like a cosmic loan. The black hole borrows energy from the virtual particle pair. If one particle falls in, the black hole effectively pays back that energy by losing a tiny bit of its own mass to the escaping particle. Over vast stretches of time, this continuous process of emitting particles causes the black hole to slowly shrink, to evaporate, to experience a slow evaporation from the abyss. As you breathe softly and deeply, Let this profound idea settle. This faint escape, this subtle glow, is incredibly weak for most black holes. For a stellar-massed black hole, it would take far longer than the current age of the universe for it to completely evaporate. A black hole with the mass of our Sun would take an unimaginable 1067 years to disappear, a number so vast it's almost meaningless to our minds. However, for very tiny, hypothetical black holes, micro-black holes, this evaporation could happen much faster, potentially even in a fraction of a second, ending in a final burst of energy. This is a paradox of warmth from cold, as the black hole, which is fundamentally cold because nothing can escape it, emits a thermal radiation, a kind of heat. As it slowly shrinks, this concept of Hawking radiation is a cornerstone of modern theoretical physics, even though it has not yet been directly observed. Its existence would reconcile black holes with the laws of thermodynamics, suggesting that they are not ultimate sinks of information, but rather incredibly slow radiators. It hints at a final, gentle fade for even the most powerful objects in the universe. Consider an ice cube slowly melting in a vast, cold room. It's losing its mass, bit by bit, through a subtle exchange of energy with its environment. Hawking radiation is a similar process, but on a cosmic scale, where the melting happens over timescales that dwarf the age of the universe. The implications of Hawking radiation are immense. It suggests that black holes are not eternal, but have a finite lifespan. It also raises profound questions about the nature of information. If a black hole evaporates, what happens to all the information about the matter that fell into it? Is it truly lost, or is it encoded in the Hawking radiation in some subtle way? This is known as the information paradox, one of the deepest unsolved problems in physics. As you drift deeper into slumber, allow your mind to contemplate this faint escape. It is a reminder that even the most formidable forces in the universe are subject to the subtle laws of quantum mechanics. It is a testament to the universe's capacity for both immense power and delicate, long-term processes. This tiny glimmer of escape from the dark is a beautiful thought, suggesting that nothing in the universe is truly permanent, not even black holes. Everything is part of a grand, evolving cycle of energy and matter, constantly transforming and subtly interacting. The next time we meet in this quiet space, we will turn our gaze to the largest of these cosmic architects, the supermassive giants that silently sleep at the heart of every galaxy, anchoring billions of stars in their gravitational embrace. Asterisk, as you continue to drift, softly, peacefully, let your mind now expand to the grandest scale of black holes. We have explored their individual power, their event horizons, and even their faint, theoretical evaporation. Now, imagine a colossal giant, silently sleeping at the very heart of every galaxy, including our own Milky Way. These are the super black holes, the true galactic hearts. Imagine a vast, swirling city of stars, billions upon billions of suns, stretching across immense cosmic distances. This is a galaxy, and at its very center, anchoring this entire celestial metropolis, is a single, unimaginably massive black hole. These giants are not formed from the collapse of individual stars. They are millions, or even billions, of times more massive than our Sun. These supermassive black holes anchor billions of stars, their gravity immense. Their gravitational pull is so powerful that it dictates the orbits of stars throughout the entire galaxy. Without these central behemoths, galaxies might not have formed, or would have dispersed long ago, their stars scattering into the vast emptiness of intergalactic space. They are the quiet centers of cosmic dance, holding galaxies in their embrace, orchestrating the graceful, swirling motion of billions of suns. Think of a giant, invisible magnet at the core of a swirling cloud of iron filings. The magnet itself is still, but its immense force organizes the filings into a beautiful, spiraling pattern. The supermassive black hole is like this invisible magnet, its gravity silently orchestrating the complex, elegant dance of stars, gas, and dust within its galaxy. Our own Milky Way galaxy, the cosmic home we inhabit, has a supermassive black hole at its center, known as Sagittarius A, pronounced A*. It's about 4 million times the mass of our Sun, yet it's confined to a region smaller than the orbit of Mercury. We can't see it directly, but we observe its presence by watching the stars closest to it. These stars whip around Sagittarius A* at incredible speeds, their orbits revealing the immense unseen gravitational pull at the galactic core. As you breathe softly and deeply, let this profound image settle. These supermassive giants are not just passive anchors, they are also incredibly active, particularly when they are feeding. When gas and dust spiral into them, they form an incredibly hot, luminous disk called an accretion disk. This disk can glow brighter than an entire galaxy, emitting powerful X-rays and gamma rays that can be detected across billions of light years. Sometimes, these supermassive black holes also launch powerful jets of plasma, streams of energetic particles that shoot out from their poles at nearly the speed of light. These jets can extend for millions of light years, influencing the formation of stars and the evolution of galaxies far beyond the black hole's immediate vicinity. They are like cosmic geysers erupting from the galactic heart, shaping the universe on the grandest scales. Consider a grand cosmic city. The supermassive black hole is its central power plant, sometimes dormant, sometimes flaring with immense energy, influencing the city's growth and development over vast stretches of time. Its immense gravity is the foundation upon which the entire galactic structure is built. Scientists study these galactic hearts using powerful telescopes that can peer into the dense, dusty centers of galaxies. They use radio telescopes to observe the jets, X-ray telescopes to see the glowing accretion disks, and infrared telescopes to penetrate the dust and observe the stars orbiting the black hole. These observations provide compelling evidence for their existence and their profound influence on galactic evolution. As you drift deeper into slumber, allow your mind to contemplate these supermassive giants. They are a testament to the universe's capacity for scale, for creating objects of unimaginable mass and power. They are the silent, powerful engines that drive the evolution of galaxies, nurturing cosmic growth even as they consume matter. This quiet center of cosmic dance, holding galaxies in its embrace, is a reminder that even the most destructive forces in the universe play a vital role in its grand, evolving story. They are not just cosmic vacuum cleaners, they are fundamental architects of the universe's structure. The next time we meet in this quiet space, we will explore the dramatic origins of these dark giants, delving into the spectacular deaths of stars that give birth to these cosmic enigmas, as we consider the birth of darkness from collapsing stars. As you continue to drift, softly, peacefully, let your mind now turn to the dramatic origins of some black holes. We have explored the supermassive giants at galactic centers. Now, we focus on the birth of smaller, yet still incredibly powerful black holes, those formed from the spectacular deaths of individual stars. Imagine a star's final breath, a magnificent, fiery collapse. Stars, like our sun, are immense balls of hot, glowing gas, powered by nuclear fusion in their cores. This fusion creates an outward pressure that perfectly balances the inward pull of gravity, keeping the star stable for billions of years. But stars, like all things, have a lifespan. When a star runs out of its nuclear fuel, its delicate balance is disrupted, leading to a dramatic end. For the largest suns, those that are many times more massive than our own, this end is truly spectacular. When they exhaust their fuel, the outward pressure from fusion ceases. There is nothing left to resist the crushing force of their own immense gravity. The star begins to collapse inward, rapidly, inexorably. This is a magnificent, fiery collapse, a cosmic implosion of unimaginable scale. Think of a giant balloon, slowly deflating, but instead of air escaping, its very substance is being pulled inward by an invisible, irresistible force. As the star collapses, its core becomes incredibly dense, hotter and hotter, until it reaches a point where even the atoms themselves are crushed. The electrons are forced into the protons, creating neutrons, and the core becomes a superdense ball of neutrons. This initial collapse can trigger a colossal explosion known as a supernova. For a brief, glorious moment, the dying star can outshine an entire galaxy, blasting its outer layers into space, enriching the cosmos with heavy elements forged in its fiery core. This is the magnificent, fiery end that gives birth to new possibilities in the universe. But for the most massive stars, even the outward blast of a supernova isn't enough to stop the core's collapse. If the remaining core is more than about 3 times the mass of our Sun, even the resistance of densely packed neutrons isn't enough to withstand the overwhelming gravity. The collapse continues, relentlessly, beyond the neutron star stage. When this happens, the core shrinks further, crushing itself down to an infinitesimally small point, a singularity. This is when it leaves behind a seed of ultimate gravity, a newly formed black hole. It's a violent birth of darkness, a new cosmic enigma emerging from the light of a dying star. The very light that once shone brightly from the star is now trapped, unable to escape the black hole's immense gravitational pull. As you breathe, softly and deeply, let this profound image settle. The birth of a stellar mass black hole is a testament to the extreme power of gravity and the dramatic life cycles of stars. It's a reminder that even the most luminous objects in the universe can give rise to the darkest and most mysterious. Consider a giant cosmic hourglass. The sand flows steadily for billions of years, representing the star's life. But when the last grain of fuel falls, the hourglass flips, and the star's core rapidly collapses, forming the tiny, dense seed of a black hole at its base. Scientists observe these stellar collapses indirectly. They look for the telltale signs of supernova, the sudden, brilliant flashes of light in distant galaxies. They also search for binary star systems, where a visible star orbits an unseen companion that has an immense gravitational pull, a strong indicator of a stellar mass black hole. These observations allow them to piece together the dramatic story of how these dark objects are born. As you drift deeper into slumber, allow your mind to contemplate this violent birth of darkness. It is a place where the familiar cycle of star life and death takes an extreme turn, leading to the creation of objects that warp space-time in profound ways. It is a humbling reminder of the universe's capacity for both immense beauty and overwhelming force. This new cosmic enigma emerging from light is a powerful testament to the universe's constant transformation. But beyond these stellar mass black holes and the supermassive giants, there are whispers of even tinier, more elusive forms of darkness. As we continue our journey, we will explore the intriguing possibility of micro black holes, tiny terrors that might be remnants of the universe's earliest moments. Asterisk, as you continue to drift, softly, peacefully, let your mind now shrink its focus to the smallest possible scale of black holes. We have explored the colossal supermassive giants and the stellar mass black holes born from dying stars. Now, imagine whispers of tiny, primordial darkness, objects so incredibly small that they defy our everyday imagination. These are micro black holes. Imagine a black hole not the size of a city or a star, but perhaps the size of an atom, or even smaller, the size of a proton. These are not formed from collapsing stars. Their existence is purely theoretical, remnants of the universe's dawn, born in the extreme conditions of the Big Bang itself. In the very early moments of the universe, conditions were incredibly hot and dense. Scientists hypothesize that tiny fluctuations in density during this chaotic period could have been so extreme that they compressed matter into incredibly small, yet incredibly dense, black holes. These would be primordial black holes, born not from stellar collapse, but from the very fabric of the nascent cosmos. Think of a boiling pot of water. As it boils, tiny bubbles constantly form and burst. In the early universe, the boiling energy could have been so intense that it briefly created these incredibly dense, tiny pockets of gravity. These micro black holes, if real, are like cosmic fossils, preserving a tiny piece of the universe's earliest, most extreme moments. These tiny terrors, if they exist, would be very different from their larger cousins. Because of their small size, their event horizons would be incredibly tiny, and the gravitational gradient across them would be immense. Any object approaching them would be spaghettified almost instantly. However, their most remarkable feature, according to Stephen Hawking's theory, is their evaporation. Remember Hawking radiation, the faint glow that black holes emit? For micro black holes, this effect would be dramatically amplified. The smaller a black hole, the faster it evaporates. A micro black hole the size of a proton would evaporate almost instantaneously, releasing a burst of high-energy particles. One the size of a mountain, still tiny by cosmic standards, would evaporate over billions of years, but still much faster than stellar mass black holes. As you breathe, softly and deeply, let this profound idea settle. The existence of micro black holes is a fascinating possibility that hints at extreme physics, pushing the boundaries of our understanding even further. They represent a fleeting, powerful presence in the fabric of space, a link to the universe's earliest, most fundamental conditions. Consider a tiny, incredibly powerful spark. It appears for a fraction of a second, releases a burst of energy, and then vanishes. A micro black hole would be like that, but a spark of pure gravity. A fleeting glimpse into the universe's most extreme densities. Scientists are actively searching for evidence of these primordial black holes. They look for the characteristic bursts of gamma rays that would be emitted during their final moments of evaporation. While no definitive evidence has been found yet, the search continues, as their discovery would provide invaluable clues about the Big Bang and the nature of gravity at its most extreme. The existence of micro black holes could also have other intriguing implications. Some theories propose they could be a component of dark matter, the mysterious invisible substance that makes up most of the universe's mass. Others even speculate about their potential use in advanced future technologies, though this remains firmly in the realm of science fiction for now. As you drift deeper into slumber, allow your mind to contemplate these tiny terrors. They are a reminder that the universe holds mysteries at every scale, from the supermassive giants to the infinitesimally small. They are a testament to the universe's capacity for both immense power and incredibly delicate, fleeting phenomena. This fleeting, powerful presence in the fabric of space is a tantalizing thought, suggesting that the universe might be even stranger and more complex than we can currently imagine. But if black holes can warp space and time so profoundly, could they also create pathways through the cosmos, cosmic shortcuts that bend reality to our will? As we continue our journey, we will explore the intriguing, theoretical possibility of wormholes and warped paths. As you continue to drift, softly, peacefully, let your mind now stretch beyond the known into the realm of theoretical possibilities. We have explored how black holes profoundly warp space-time, bending light and slowing time. Now we consider an even more mind-bending idea that emerges from this extreme warping: the concept of wormholes, theoretical tunnels that could act as cosmic shortcuts, bending reality to our will. Imagine taking a piece of paper and drawing two dots far apart. On its surface, the only way to get from one dot to the other is to travel across the paper. Now, imagine folding that paper so the two dots touch. If you could then poke a hole through both dots, you would create a shortcut, a tunnel directly connecting them, bypassing the long distance across the surface. This is a simple analogy for a wormhole, a theoretical tunnel through space-time that could connect to distant points in the universe, or even to different points in time. Could the extreme warping of space-time create secret passages? According to Einstein's theory of general relativity, the equations that describe gravity and space-time do allow for the theoretical existence of such shortcuts. These wormholes, sometimes called Einstein-Rosen bridges, are essentially hypothetical tunnels through the cosmos, connecting distant points in a way that would dramatically reduce travel time. Think of it like a shortcut through a mountain. Instead of climbing over the peak, you could theoretically tunnel straight through, arriving at your destination much faster. Wormholes would be the ultimate cosmic shortcuts, allowing for interstellar travel across vast distances in a fraction of the time it would take to travel through normal space. However, there's a significant catch. While the equations allow for them, these theoretical wormholes would be incredibly unstable. They would likely collapse almost instantaneously, faster than anything could travel through them. To keep a wormhole open and stable for travel, you would need exotic matter, matter with negative energy density, something that has not yet been observed and may not even exist. So, while wormholes are a dream of cosmic shortcuts, bending reality to our will, they remain firmly in the realm of theoretical physics and science fiction for now. They are a fascinating consequence of the extreme warping of space-time, but their practical existence and stability are highly speculative. As you breathe softly and deeply, let this profound idea settle. The very idea that space-time could be folded and connected in such a way is a testament to the mind-bending nature of gravity at its most extreme. It suggests that the universe might have hidden pathways, secret routes that defy our conventional understanding of distance and travel. Consider a crumpled piece of paper. Two points that were far apart on the flat sheet can become very close when the paper is crumpled. If you could then tunnel through the crumpled paper, you would have a shortcut, Wormholes are like this, but with the fabric of space and time itself being crumpled and connected. Scientists continue to explore wormholes theoretically, not necessarily because they expect to find one for travel soon, but because studying them helps to push the boundaries of our understanding of gravity, space-time, and the fundamental structure of the universe. They are thought experiments that help physicists explore the limits of Einstein's theories and search for new physics beyond them. As you drift deeper into slumber, allow your mind to contemplate these warped paths. They are a reminder that the universe holds possibilities that stretch far beyond our current technological capabilities and even our current understanding. They are a testament to the universe's capacity for both immense power and incredibly intricate theoretical structures. This dream of cosmic shortcuts, bending reality to our will, is a powerful inspiration for both scientists and dreamers. It reminds us that the universe is full of hidden potential, waiting to be discovered, or perhaps waiting for us to discover how to manipulate its deepest laws. But even if wormholes remain theoretical, black holes themselves pose a profound, real puzzle about information. For as we continue our journey, we will explore the black hole information paradox, a mystery of what the universe remembers and what might be lost forever. As you continue to drift, softly, peacefully, let your mind now settle on one of the deepest, most perplexing puzzles in all of physics, a mystery posed by black holes themselves. We have explored their immense gravity, the event horizon, and even their theoretical evaporation through Hawking radiation. Now, we confront a profound question: what happens to all the information about what falls within? This is the black hole information paradox. Imagine taking a book filled with countless stories, poems, and facts, and throwing it into a black hole. In our everyday world, if you burn a book, its information isn't truly lost. It's just scrambled. In the smoke and ash, theoretically recoverable if you had enough knowledge and tools. The laws of physics, particularly quantum mechanics, tell us that information is never truly destroyed. It is always conserved, merely transformed. But when something falls into a black hole, it seems to vanish forever beyond the event horizon, to be crushed into the singularity. And if the black hole then slowly evaporates through Hawking radiation, emitting a generic thermal glow that doesn't seem to carry any specific details about what fell in, then where does the information from the book go? Does it simply disappear from the universe? This is the core of the paradox. Information, once thought eternal, seems to vanish into the dark. If information is truly lost, it would violate one of the most fundamental principles of quantum mechanics, a principle that underpins our entire understanding of the universe. It challenges physics' deepest laws, creating a profound conflict between general relativity, which describes black holes, and quantum mechanics, which describes information conservation. Think of a cosmic shredder. You feed a document into it, and it seems to disappear. But if the shredder is truly a black hole, and it then evaporates, does the shredded information simply cease to exist? This is the mystery of what the universe remembers. If the information is truly gone, then the universe is not deterministic in the way quantum mechanics suggests. As you breathe softly and deeply, let this profound puzzle settle. It's a question that has occupied the minds of the greatest physicists for decades, including Stephen Hawking, who initially believed information was lost and later changed his mind. The stakes are incredibly high, as resolving this paradox could lead to a deeper, unified theory of gravity and quantum mechanics, Consider a giant cosmic library. Every book, every piece of knowledge, every particle that has ever existed is a piece of information. If a black hole truly destroys information, then it's like a cosmic librarian who simply burns books without keeping any record of their contents, a violation of the universe's own meticulous accounting. There are several proposed solutions to this paradox, each more mind-bending than the last. Some suggest that the information is not truly lost, but is somehow encoded in the subtle fluctuations of the Hawking radiation, like a holographic image on the event horizon itself. Others propose that the black hole might leave behind a tiny, stable remnant that holds the information. Still others suggest that perhaps information is not lost, but simply becomes inaccessible, residing in a baby universe that branches off from our own. None of these solutions are fully proven or universally accepted, and the black hole information paradox remains one of the most active and fascinating areas of theoretical physics. It is a testament to the universe's capacity to challenge our most fundamental assumptions and to push the boundaries of human intellect as you drift deeper into slumber. Allow your mind to contemplate this mystery of what the universe remembers. It is a reminder that even in the most extreme corners of the cosmos, there are profound questions about the nature of reality, about what is truly fundamental, and about the very essence of existence. This mystery of what the universe remembers is a quiet, profound puzzle that continues to inspire. It reminds us that our understanding of the cosmos is always evolving, always deepening, and that there is always more to discover, even in the darkest corners. As we conclude our journey through the wonders of black holes, let the immensity of these cosmic questions and the beauty of the universe's intricate design gently guide you into the deepest, most peaceful slumber. For in the boundless embrace of the cosmos, all mysteries find their quiet rest.